In this work, we present a conceptual and computational framework to define notions of fairness for rankings. Rankings are ubiquitous in the online world today, and we have transitioned from searching books in the library to ranking products in an online marketplace, or ranking opinions, jobs, job applicants, friends, and even potential romantic partners. With the growing number of applications, there is also a growing awareness that ranking systems have a responsibility not only to their users but also to the items or subjects that are being ranked. Consider an example of a job applicant ranking system. We have a set of 6 candidates who have applied for a software engineering position. Each candidate has a relevant score attached to them, that is, the fraction of employers that might find the candidate relevant for the job. To maximize the utility of the ranking for the users, that is, the employers in this case, probability ranking principle suggests that we rank these candidates in the decreasing order of their relevance. Now, let us look at the amount of exposure that each of the candidates gets. Let's say the position bias for position J is 1 divided by log 1 plus J. This is the standard position bias that is used in measures such as DCG. Now, this means that the probability of each candidate being interviewed decreases with the position as we go down the ranking. For this particular setup, it turns out that the average exposure of the two groups differs by about 0.32, while there is only a difference of 0.03 in the average relevance of the two groups. In other words, on average, 32% less number of employers are likely to interview female candidates. This disparity in opportunity occurs even with a tiny difference in the relevance scores. Is there a better way to allocate exposures than what is being suggested by the probability ranking principle? In our work, we try to answer this question. We formulate a framework where we can define the utility of the rankings for users as well as define fairness constraints for items or subjects that are being ranked. For example, consider the following constraint. We might want to make sure that the average exposure of a group of items, for example, the set of female job candidates, is proportional to the group's average relevance score. That is, the average exposure of a group divided by its average relevance is equal across groups. Since fairness goals can be application specific, we also show how a broad range of such constraints can be implemented using our framework, including constraints that avoid disparate exposure and avoid disparate impact in terms of relevance, clicks, and the position bias. Once we define such fairness constraints, we can solve an optimization problem whose solution maximizes the utility of the rankings for the users and also satisfies fairness constraints for the items. In our framework, this optimization problem is a linear program for a variety of constraints and hence can be solved efficiently. Please check out our paper Fairness of Exposure in Rankings at KDD 2018 for more details. Thank you.